Assalamu alaikum dear students. I hope you are all fine by the grace of Almighty Allah. I welcome you all to the 15th lecture of Thermodynamics 2. Lecture 15. The contents of lecture 15 are Application of Entropy Principle, Transfer of heat between two thermal energy reservoirs, Mixing of two incompressible fluids, Heat transfer between a finite body and thermal energy reservoir. Maximum work obtainable from finite body and thermal energy reservoir. Maximum work obtainable from two finite bodies. Comparative study. Numerical problems and conceptual questions and answer. Application of entropy principle. So these are some application of entropy principle. We have already studied the entropy principle in the previous lecture. Now we are studying its applications. So the first application is transfer of heat between two thermal energy reservoirs. So we have already studied what is meant by thermal energy reservoir. A thermal energy reservoir is a body which have an approximately infinite heat capacity and its temperature remain constant. So usually the atmosphere or ambient air is taken as thermal energy reservoir, or for the combustion or high temperature, the combustion chamber that supply heat at constant rate is also considered thermal energy reservoir. So transfer of heat between two thermal energy reservoir. Mixing of two fluids. So another application of entropy principle is what happens to the entropy when two fluids intermix with each other. So third application is maximum work obtainable from a finite body and thermal energy reservoir. So we will connect a finite body, or to differentiate thermal energy reservoir body with the simple body, we have used the word finite. So in the book the finite body word is written, so we will use the same. So as you know, when two bodies are connected and in between there is a heat engine and one body is at high temperature, so the work will be produced by a heat engine. So in the third application we will be calculating the maximum work that can be obtained when a heat is flowing from a finite body into a thermal energy reservoir. The fourth application of entropy principle is maximum work obtainable from two finite bodies at temperature T1 and T2. So here we have two finite bodies, whereas in the previous example we have one finite body and other is thermal energy reservoir. But in the fourth application we have two finite bodies that are at a different temperatures of T1 and T2. So the extension of application of entropy principle is we will be studying process exhibiting external mechanical irreversibility. So the first application of entropy principle is transfer of heat between two thermal energy reservoir. So on the right hand side you are seeing thermal energy reservoir A that is at a temperature of T1, and on the right hand side you are seeing thermal energy reservoir B that is at a temperature T2. So as mentioned that all bodies are completely insulated, as mentioned uh, at the top of the figure, that insulation is provided at the entire body. So both the thermal energy reservoir are insulated, and the path connecting both the thermal energy reservoir are is also insulated. So as the direction suggests that heat is flowing from left to right, that is from thermal energy reservoir A to thermal energy reservoir B. So that means T1 is greater than T2. So case 1, assume T1 is greater than T2. So here are some mathematics. So we already know that S is used to represent entropy. So del S means change in entropy is minus Q T1 and over Q over T1, and for thermal energy reservoir B, the change of entropy is given by Q by T2. So T1 is the temperature of thermal energy reservoir A and T2 is the temperature of thermal energy reservoir B. So as the amount of heat is leaving thermal energy reservoir A and entering into thermal energy reservoir B, that way the change of minus sign or negative sign is represented with the entropy of thermal energy reservoir A. So negative sign is as Q is leaving thermal energy reservoir A and entering into thermal energy reservoir B. So as heat is reducing, so negative sign is represented to show that heat is leaving the system. So the formula for change of entropy of universe is del S universe is equal to del S system plus change of entropy of surrounding. So del S is change of entropy of universe is equal to change of entropy of system plus change of entropy of surrounding. So as the arrow suggests, and in the box it is written that change of entropy of surrounding is zero due to insulation. As no heat is entering or leaving the system, therefore the change of entropy of surrounding will be equal to zero. So the change of entropy of universe will only be equal to change of entropy of the system. Change of entropy of universe is equal to change of entropy of the system. So we have two individual system or parts, that is part A for thermal energy reservoir A and part B is del SB is for thermal energy reservoir B. So change of entropy of universe is equal to change of entropy of the system, that is change of entropy of A plus change of entropy of B. We have already calculated or represented these entropies at the top, that del S is equal to minus Q over T1 and del SB is equal to Q over T2. So we will insert these value, and change of entropy of universe is equal to minus Q over T1 plus Q over T2. So taking Q common, change of entropy is equal to Q bracket 1 over T2 minus 1 over T1. And after simplification we get that relation. So as at the top we have taken here LCM T1 T2, and in the numerator you can see T1 minus T2. So that sign will suggest that what is the overall value for the change of entropy of the universe. So the numerator value suggests that T1 minus T2 is positive as T1 is greater than T2. So we have assumed that T1 is greater than T2. Therefore, the value of numerator will be positive, and the value of overall polynomial will also be equal to positive value. So del S universe is a positive value. So in the previous lecture we have discussed about the values for there are three values. Change of entropy is positive, then it is a irreversible process. For change of entropy is equal to 0, that is a reversible reaction, and for change of entropy is negative, that is impossible process. I will write it here. For del S is greater than 0, possible process. And irreversible. Del S is equal to 0, reversible. And del S is less than 0, that is impossible. So you must remember these 3 points. So when you will be solving certain numericals, sometimes the value of entropy will be greater than 0. So you will write that is an irreversible process. For entropy calculation that comes out to be 0, that means that the process is reversible. Whereas if del S value comes out to be negative or less than 0, that is an impossible process. So here you can also write universe as well. So that is del S universe. Now case 2. So in case 2 we are assuming that T1 and T2 both are equal. So the temperature of thermal energy reservoir A, that is T1, and thermal energy reservoir temperature B, that is T2, both are equal. So in that case the change of entropy of the universe is equal to 0. So as already discussed in the previous slide, that for change of entropy of universe that is equal to 0, that means that is a reversible process. So for case 3 we again assume that T1 is greater than T2 and heat is flowing from T2 to T1, that is in the opposite direction. So I will mention it here as well. So that means heat is flowing in the opposite direction. So heat is temperature of thermal energy reservoir is T1 and thermal energy reservoir B is T2, but the direction of heat flow is opposite. So if we calculate the entropy of case 3, that comes out to be less than 0. That means it is an impossible process. So as you know that if T1 is greater than T2, so the direction of heat flow must be from left to right. Whereas in the statement it is suggested that the direction of flow is from right to left, that is from thermal energy reservoir B to thermal energy reservoir A. That is impossible. So if we prove that with the help of change of entropy principle that comes out to be less than 0, that also suggests that it is also an impossible process. So the second application of entropy principle is mixing of two incompressible fluids. So here is a schematic diagram. So on the left hand side we have an incompressible fluid A that has a mass m1, heat capacity C1 and temperature T1. On the right hand side we have an incompressible fluid B that has mass m2, specific heat C2 and temperature T2. At the center we have a partition and the entire body is insulated as mentioned at the top of the schematic diagram, and T1 is greater than T2. That means incompressible fluid A is at a higher temperature and incompressible fluid B is at lower temperature. So the first point is A and B are not thermal energy reservoir. So these are two simple bodies. So these are not thermal energy reservoirs. When partition is removed, both fluids will mix together. So as we remove the center partition, the both fluid will intermix with each other. So the final mass will be mass of fluid A plus mass of fluid B, that is m1 plus m2. So as T1 is the higher temperature and T2 is the lower temperature, so when they will mix together, they will approach an intermediate temperature. So here we have written that is the final temperature. So T1 or mass fluid A temperature will approach TF and fluid B temperature will also approach TF. So TF will be greater than T2 but less than T1. So here it is also mentioned that the final temperature TF is less than T1 and greater than T2. So for example, the temperature T1 is 100 degrees centigrade and temperature T2 is 50 degrees centigrade. When the partition is removed, so both fluid will intermix with each other. So the final temperature will lie somewhere between 100 and 50. For example, let the final temperature will be 70 degrees centigrade. So 70 will be less than 100 and greater than 50. So when partition is removed, so there will be a change in the entropy for body A. So change of entropy of fluid A is written by integration sign T1 to TF. So T1 is the initial temperature and TF is the final temperature for fluid A. So dq by dt is a mathematical representation of entropy. So for fluid A, dq is replaced by m1 c1 dt because m1 is the mass of fluid A and c1 is the specific heat. So you should remember that for incompressible fluid we have only one specific heat. So m1 c1 dt divided by t. So m1 and c1 are both constant, so they will come out of the integration sign, and when we will integrate 1 over dt, that is has the same integration of 1 over x dx, that is natural log of x. So in our case we have natural log of t. So t1 is the lower limit and tf is the upper limit. So the next step is m1 c1 natural log tf minus t1. So here we have utilized the property of log and write the negative terms or difference term that was Tf minus T1. So here we have utilized the property of log and write it in the fraction. So change of entropy of fluid A is equal to m1c1 natural log Tf over T1. Similarly, when we will be calculating the change of entropy for the fluid B, the same mathematical symbol that for the initial temperature is T2 and the final temperature is Tf. So dq by T m C2 natural log Tf over T2. So m2 is the mass of fluid B, C2 is the specific heat of fluid B, and the natural log Tf over T2, T2 is the initial temperature of fluid B. So here is our main equation for change of entropy of universe is equal to change of entropy of system plus change of entropy of the surrounding. Now as mentioned in the schematic as well, so due to insulation the change of entropy of the universe is equal to 0. So change of entropy of universe will be equal to change of entropy of the system. So our system comprises of two parts, that is A fluid for fluid A and B for fluid B. So change of entropy of universe is equal to change of entropy A plus change of entropy B. We have already calculated these del SA and del SB. So change of entropy of universe is equal to M1 C1 natural log Tf over T1 plus M2 C2 natural log Tf over T2. So the entire equation there is no negative sign, so change of entropy of universe will be positive value. So this calculation suggests that this process is a possible process and this is also an irreversible process. So in the examination point of view, you might be asked that show that for the process of mixing of two incompressible fluid, that is an irreversible and possible process. So with the help of entropy principle, so you will have to draw that schematic diagram as well and perform that mathematical steps to show that first you will calculate individual entropy of fluid A and individual entropy of fluid B, then you will write the main equation for the entropy principle. So change of entropy of universe is equal to change of entropy of system and surrounding. So then you will say that due to insulation that the change of entropy of surrounding is equal to 0. Then you will put the value of change of entropy of fluid A and change of entropy of fluid B in the main equation, and then you will calculate that the value of the equation is positive, and that show that the process is irreversible and that is also a possible process. So for final temperature, so here we are using the law of conservation of heat. So heat lost by A is equal to heat gained by B. So T1 is the initial temperature of fluid A and T2 is the initial temperature of fluid B. T1 is greater than T2. Therefore, when both fluid will intermix with each other, the final temperature will be somewhere in between T1 and T2. Final temperature will be less than T1 and greater than T2. So here we want to find the final temperature. So QA is written by mCp delta T. So T1 minus Tf, and for fluid B that is M2C2 Tf minus T2. So rearranging the mathematical equation, taking Tf common on one side, and this is the relation of finding the value of final temperature, that is m1 c1 t1 plus m2 c2 t2 divided by m2 c2 plus m1 c1. So m1 is the mass of fluid A, c1 is the specific heat of fluid A, t1 is the initial temperature of fluid A, m2 is the mass of fluid B, c2 is the specific heat of fluid B, T2 is the initial temperature of fluid B. So M2 and C2 are mass and specific heat of fluid B respectively, and M1 C1 is the mass and specific heat of fluid A. So when you will put all these value in the relation, then you can calculate the final temperature of the fluid after mixing. So here is a case when M1 is equal to M2, that is both fluid have same mass. So M1, that is the mass of fluid A, and M2, that is the mass of fluid B, they both are equal. So we have represented the equal value with a single value, that is M, and both have same specific heat, that is C. So C1, that is the specific heat of fluid A, C2, that is the specific heat of fluid B, they both have same value. So we have represented that with a single specific heat, that is C. So here it is also written when both fluids have same mass and same specific heats. So the relation for the final temperature is reduced to mc T1 plus T2 divided by 2 mc, and both mc will cancel out, so T1 plus T2 divided by 2. So the final temperature will be the average of both temperatures. So change of entropy of universe is mc natural log Tf over T1 plus natural log Tf over T2. So here we have used the property of natural log. So we have taken log outside of the bracket, and for the addition sign we have converted into the multiplication. So here we have used the property of log. So change of entropy of universe when both fluid have same mass and both fluid have same specific heat, then the change of entropy of universe can be calculated by mc natural log Tf square divided by T1 T2. Tf can be calculated by T1 plus T2 whole divided by 2. So that is the average value for T1 and T2. So here we have taken the square outside the bracket. So under root sign is introduced to when the square will multiply here. So under root sign will cancel out with the square sign. So del S universe or change of entropy of universe is mc natural log Tf divided by T1 T2 under root whole square. So here we have also utilized the property of log. So the square or power come out at the left hand side and multiplied with the relation. So that 2 that is in the power is now in the multiplication. So change of entropy of universe is equal to 2 mc natural log Tf over T1 T2. So here we have put the relation of Tf, that is here Tf is equal to T1 plus T2. So here we have replaced the value of Tf, that is T1 plus T2, for same mass and same specific heat. So here that was T1 plus T2 divided by 2, that is a arithmetic mean, and T1 T2 under root, that is a geometric mean. So here it is also written that arithmetic mean is AM is equal to T1 plus T2, whereas geometric mean is mathematically represented by under root T1 T2. So mathematically we know that the value of arithmetic mean is greater than geometric mean. So therefore the change of entropy of universe is greater than 0. So this represents that this is a possible process and this is also an irreversible process. So the third application for entropy principle is heat transfer between a finite body and thermal energy reservoir. On the right hand side, two bodies are shown. So on the left side body is, that is written as body A. So body A is at a temperature T, specific heat C and mass M. And on the right hand side, thermal energy reservoir is shown, that is at a temperature T naught. So T, that is the temperature body A, is at a higher temperature, therefore heat is flowing from left to right. And on the top of the schematic diagram, it is mentioned that the entire body is insulated. So there is no heat interaction between the surrounding and the system. So the main equation, that del S universe is equal to change of entropy of surrounding plus change of entropy of system. So here the change of entropy of surrounding will be equal to 0, as the insulation is there to avoid heat reaction between system and surrounding. So the term on the right hand side, that is del S surrounding or change of entropy of surrounding, will be equal to 0. So the change of entropy of universe is equal to change of entropy of system, that is equal to change of entropy of A plus change of entropy of B. So change of entropy of universe, so del S A is represented by integration sign, lower limit and upper limit. So T is the initial temperature of body A, so lower limit is the initial temperature of body A, and T naught is the final temperature. So heat is moving, so mass will acquire the temperature of the thermal energy reservoir, whereas the entropy of thermal energy reservoir is represented by Q by T. So here the temperature of thermal energy reservoir is T naught, so the entropy of thermal energy reservoir is Q by T naught. So here MC are constant, so that will come out of the integration sign, and the term left will be 1 by t dt. So when we will take integration of 1 by t dt with the lower limit and upper limit of t and t naught, then we have natural log of t with lower limit t and upper limit t naught. When we will insert the upper and lower limit in the natural log t function, that will be T naught minus T. We have used the log property to represent it in the fractional form, that is T naught over T. So this is the final form of this integration sign, that is mc natural log T naught over T, whereas the entropy of change of entropy of B will remain same, that is U by T naught. So in the entire relation there is no negative sign and all values are positive. Therefore the change of entropy of universe will also be a positive value. So that suggests that the change of entropy of universe for heat transfer between finite body and thermal energy reservoir is an irreversible process and possible process. So in this slide there was a repetition of certain steps. So we have I have told you each step individually. So I didn't have written all the steps, so that the change of entropy of surrounding is equal to 0. So we have calculated in previous slide, we have calculated these step before and then insert these value in the main equation. So in this slide we have shortened those steps as well. So fifth application for the entropy principle is maximum work obtainable from finite body and thermal energy reservoir. So on the top right side you can see the schematic diagram of body A and thermal energy reservoir. So body A is at a temperature T, specific heat C and mass M. So heat is flowing from body to thermal energy reservoir. So now we are calculating the maximum work. So here we have installed a heat engine. So the function of heat engine is to convert thermal energy into mechanical work. So here body A is acting as a source, that because it has a temperature that is greater than thermal energy reservoir. So a heat will flow from body A, will enter into heat engine. Some of that thermal energy will be converted into work, that is represented by W. So the left thermal energy will be ejected into thermal energy reservoir, that is at temperature T naught. So insulation is written at the top of schematic diagram. That means the entire system is insulated and there is no heat interaction between system and surrounding. So change of entropy for body A is written as mc natural log T naught over T. So here you know that the main equation was integration sign. So I will write. So the step previous to that step is, so the previous step is integration sign, initial temperature, final temperature is T naught, M MC 1 over T dt. So then we MC comes out at the left hand side and 1 over dt is a natural log. So upper limit over lower limit. And the change of entropy for thermal energy reservoir, that is, here we have represented it with B. So change of entropy is Q minus W divided by T. So because Q minus W is the heat that is coming inside the thermal energy reservoir, so Q minus W is the amount of heat divided by T naught is the temperature of thermal energy reservoir. So as you can remember that in the previous slide where that heat engine was not present, the value for the entropy was written by Q by T naught. So here as the lesser amount of heat, so because that thermal energy, some of that thermal energy is converted into work. So let's suppose 100 kilojoule was entering into the system, entering into the heat engine, and 50 kilojoule is converted into work, and other 50 is that is rejected into the thermal energy reservoir. So Q minus W is the lesser amount of thermal energy that is entering into the thermal energy reservoir. So change of entropy of B is Q minus W divided by T naught. Del S surrounding is equal to 0 due to insulation, and change of entropy of universe is equal to, that is greater than equal to 0. That is the main equation. So here we have inserted the value of del SA plus del SB because we want to calculate the value of W. So after simplification, so the value of Q is MC T naught, T minus T naught, because T is the higher temperature and T naught is the lower temperature. So we will insert that relation into the main equation, and the relation for maximum work is, that is less than or equal to MC bracket T naught natural log T naught over 2 T plus T minus T naught. So here M is the mass of body A, C is the specific heat, T is the temperature of body A, and T naught is the temperature of thermal energy reservoir. So that is the relation for maximum work obtainable from finite body and thermal energy reservoir. Now we will calculate maximum work obtainable from two finite bodies. So in the upper figure, on the left hand side, that is body A, that is a temperature T1, and on the right hand side, that is body B, that is a temperature T2. So as these bodies are not thermal energy reservoir, therefore their temperature will, after some time, their temperature will reduce because heat is flowing out of these bodies. So the initial temperature of body A is T1, and as heat is flowing from body 1, heat is flowing outside of the body 1, that is T1, and entering, some of that heat is converting into work, and uh, rest of that energy is entering into body B, that is at a lower temperature T2. So as the heat will keep on flowing unless they both came at equilibrium temperature. So for example, at initial the temperature of body A is T1, that for example is 100 degrees centigrade, and temperature of body B T2, for example, that is 50 degrees centigrade. So let's suppose that initial, that is 100 degrees centigrade, and that is 50 degrees centigrade. So heat is flowing from here left to right. So the temperature that is initially at the 100 degrees centigrade will drop, and as the heat is entering into the body B, so T2 temperature, that is 50, will increase. So That process will keep on going until they reach a equilibrium temperature. Let's suppose that is 70 degrees centigrade. So that process will keep on going until the temperature is 70 degrees centigrade. So from 100 to 70 and from 50 to 70. So temperature T2 will increase and temperature T1 will decrease. So the final temperature is Tf. So in the bottom figure, the final position is shown that the body A will eventually reach the final temperature, that is Tf. So in the above example, we have considered the value of Tf, that is 70. So and that is also 70. So as both have same amount of same temperature, so at that equilibrium there will be no work produced and there will be no heat transfer. So for body A, Q1 is CpT1 minus Tf, that is initial minus final temperature, and Q2 is CpTf minus T2. So for body B, the final temperature is greater than initial, so Wmax is equal to Q1 minus Q2. So Wmax is Cp T1 minus Tf minus Cp Tf minus T2. So simplifying the equation, the Wmax is Cp T1 plus T2 minus 2Tf. So we call it equation A. So as you can see that there is no, so when we will calculate the value for the entropy of universe, that comes out to be positive value, and Wmax can be calculated by Cp T1 plus T2 minus 2Tf. So now we are calculating the value for the entropy. So change of entropy of the system plus change of entropy of surrounding. So due to insulation, change of entropy of surrounding is equal to 0, and change of entropy of system is del SA plus del SB. So both bodies change of entropy are written. For M is equal to 1, the value for change of entropy of the system is written as Cp natural log Tf over T1 plus Cp natural log Tf over T2, using the property of log. So Cp is taken as common and natural log, so both addition term are multiplied. So Tf over T1 multiplied Tf over T2. So we have divided the both side with Cp, and the term left is natural log Tf square over T1 into T2. So 0 is the natural log of 1, so equating both sides. So Tf square divided by T1 into T2 is greater than equal to 1. So Tf square is greater than equal to T1 T2. We have multiplied both sides with T1 T2, and Tf comes out to be T1 T2. So this is for reversible process because Tf was greater than equal to. So for reversible process we will use the equal sign, and for irreversible process we will use the greater than sign. So for reversible process Tf is equal to T1 T2 under root, and for irreversible process Tf is greater than under root T1 T2. Now from equation A, Wmax is equal to Cp bracket T1 plus T2 minus 2Tf. That was the relation we have mentioned, we have calculated in the previous slide and marked with equation A. So when we put the here the value of Tf that we have found, so for maximum work we we know that the maximum work will be obtained by in the reversible process. So Wmax is equal to Cp T1 plus T2 minus 2 T1 T2. So here we have insert the value of Tf. So if we only know the value of two bodies T1 and T2 initial values, then we can also, we don't have to find the value of Tf. We can directly introduce the value in this relation and find the maximum work. Now here is a comparative study. So in case A, mixing of two incompressible fluid, no work is obtained. In case B, work from two bodies, that is reversible, so maximum work is obtained. And in case C, work from two bodies, that is irreversible, so work is obtained then the reversible. So if we have two bodies and the process is reversible, then maximum work is obtained. But if we have two bodies with the same temperature difference and other properties and the process is irreversible, then the work obtained will be less than the maximum work that was obtained for the reversible process. So in case A, when there we have no work obtained, so the final temperature when there was the mixing of two fluid, so here we have a final temperature, that is the final temperature after the intermixing of both fluid. So as there is no work uh, taken out from the system, so the final temperature will be maximum in case A. And in case C, when we are moving heat from one body to body A to body B and also taking W or producing work, so and work is less than the maximum work or reversible work, so that has the fluid final temperature will be lesser than case A. So final temperature fluid for case C is lesser than A and final temperature of case B will be the least because maximum work is already obtained from the system. So as maximum work is produced, therefore the final temperature for the system will be least. So there are some conceptual question answer. So first one is, how can we change S of a substance going through reversible process? From definition of entropy, ds is equal to dq by T. So for reversible process, thus only heat transfer gives a change in S. Expansion, compression involving work does not give such a contribution. So from mathematical relation, we know that the change of S is due to heat transfer, that is dq. A reversible process adds heat to a substance. So if T is varying, does that influence the change in the entropy? So ds is equal to dq by T. So the answer is yes. For reversible process, if T goes up, it means S changes less per unit of dq, and the opposite of T decrease, then S change more per unit of dq. So that means if T is increasing, then there will be a decrease in the entropy because T is in the denominator. So if T is decreasing, the change of entropy will be greater, and if T is increasing, then change of entropy with respect to change of temperature will be less. So that is your home assignment. You can read it. So thank you very much. Allah Hafiz.